Well, good morning, everyone, and welcome to Mallett Technologies webinar series for this Friday, November 9th. Appreciate you being here. Today, our presenter, again, like last week, is Steve Rugg. Steve is the Technical Service Manager here at Mallett Technology. I think most of you have either met Steve in person or worked with him over the phone. So you know how Steve works, and he also wanted to let everyone know that since this is a very interactive presentation today, I am not going to mute everyone. So if there's noise in your office, please mute yourself. But if a question comes up during the presentation, Steve asked that you can just either immediately put it in the chat box or feel free to just speak up and ask Steve a question, during his presentation. That'll be fine. I'm sure whatever question comes up will be good to help everyone else out. So today's agenda, we'll give you an overview. We'll do our meshing presentation. And then at the end, if there's any questions or discussions left, we can go over that. Again, Mallett Technology, we're a company that uses world-class engineering software tools combined with a broad knowledge and expertise to help our clients compete in today's marketplace, produce reliable and cost-effective products. We've been serving engineering customers for nearly 40 years. We actually started as an arm for Swanson Analysis Systems, which later became ANSYS, founded by Dr. Swanson as Swanson Engineering Associates Corporation in the 70s. We've been a channel partner since 1985. Our website address, of course, is mallett.com. Next week, we're going to have another webinar, and the subject for next week is going to be fatigue evaluation via modal and random vibration analysis in ANSYS. And that'll be next Friday, the 16th of November, same time, 11 a.m. Eastern Time. And also next week, we still have scheduled a in-classroom training here at Durham, North Carolina in our facility. And that's on November 14th and 15th. The subject will be basic structural nonlinearities in ANSYS Mechanical. So if anyone's interested in that, please call me or send me an email. Like normally this is being recorded. So if you'd like a link to a recording of this, just let me know. Or if you have a colleague or someone else who expressed some interest in the subject but couldn't make it, please let me know. I'd be happy to send the link to them so they can also listen to today's webinar. So with that being said, I will turn the presentation over to Steve, and we can get started.
Okay, great. So yeah, as Buzz mentioned, I'm just going to be walking through some meshing in ANSYS, kind of best practices, different options you have available to you, that kind of thing. It's going to be, let's see, the way it's going to work, I'm going to start off kind of just covering the basics, primarily different mesh methods, different size control methods, and then going into, I have a number of just like toy geometry that I built kind of to demonstrate some of the different methods. But the geometry I have is fairly basic. I'll be talking about some best practices and kind of the methods we use here at Mallett. If you're seeing something that's not applicable to your specific geometry, or if you have kind of a question about how to mesh your geometry or how to determine if the mesh is adequate or things like that, just interrupt me. We can chat about it. I'm sure it'll be helpful for the whole group, because what I'm going to present is fairly basic, but obviously it's extendable to really any range of problem complexities. The tools and the methods I'm going to go over here are pretty much what I use on a daily basis for all our consulting work. right? There are other tools that I'm not going to talk about, but I'm not going to talk about them because they much more apply to the 1% of the time usage versus the 99% of the time. Okay, so the first question, when does meshing start? Right, so truly meshing in my mind, it starts the moment geometry is created to be analyzed in FEA. So if you're receiving and or creating geometry that is, let's say has a bunch of small faces or is broken up oddly, or essentially is just of a poor quality, it's going to make it much harder to mesh, and odds are it's going to make your mesh of a poor quality as well. Right, so meshing, when you're thinking about meshing and thinking about setting a problem up for meshing properly, meshing starts the moment you have the geometry and the moment it's being created. So yeah, really a common phrase we use here at Mallett, and honestly, this is more a common phrase that we use during training classes. However, this is our philosophy at Mallett, that space claim is our primary meshing tool. Essentially, initially getting the geometry to the point we need it within space claim allows meshing to go very smoothly. If we were to neglect the amount of work we do in space claim, usually I'm spending almost equal amounts of time in space claim as I am in ANSYS. If I was to neglect the time I spend in space claim, the time I spend in ANSYS is going to increase dramatically. My problem size is going to increase dramatically. Odds are I'm going to have some poor elements that may or may not prevent the solution from running, things like that. Right. So when you consider meshing, it starts with the geometry first. And what I will say is, if you have not used space claim before, it is highly, highly recommended. There's just some built-in features that allow meshing to be done much more smoothly and easily than, let's say, if I'm importing a part from any CAD system, whether it be Creo, SolidWorks, Solid Edge, Inventor, any of those. Generally, modifying and preparing geometry in those tools is much harder, and it's not quite going to get you to the point where space claim would. So if you haven't tried it before, highly recommended. ANSYS does have training for space claim, but it is the kind of tool that to some extent you can just go in and play around with and you'll get a sense of how it works. So the next question is, why does meshing matter, right? Why do we care about meshing? First and foremost, it really determines the accuracy of your solution, right? So if you're not well versed in meshing, or if your mesh is inadequate, your solution could give you the wrong answer, even though it's set up properly. Whoever just joined, Miguel, can you mute your mic?
Sure.
Thank you. So meshing determines your accuracy, right? That's first and kind of foremost in importance. The second, right, depending on how your mesh is set up, it can make interpreting final results easier or harder. Essentially, it could increase the number of singularities in your system. It could decrease them. It could make gradients smoother. In general, if a gradient's going to be smoother, it's going to be more accurate because elements are calculating stresses or strains or displacements that are similar to the adjacent element. Meshing plays a huge role in the overall runtime of your problem, right? More elements equals greater runtime. So understanding how to mesh efficiently is a big factor in kind of optimizing your runtime. For some jobs, right, for some, let's say, static structural jobs, where it's really just one run, one iteration of solving the stiffness matrix, oftentimes you can just throw a ton of elements at it and hit solve, right, because it solves relatively quickly. But for jobs where you're going through a number of iterations, let's say a transient shock analysis or a modal analysis where you have to pull out a number of modes, those are cases where you really truly want to optimize your element sizing or the number of elements, because otherwise you're going to dramatically increase your runtime, you're going to dramatically increase your solution size, and with that comes kind of a whole slew of additional challenges. Number 4, meshing can help or hurt convergence of nonlinear simulations, so you got to pay attention to it there. And number 5, essentially, depending on how well you mesh, can increase or decrease the possibility of setup error. And here specifically, I'm referring to the work done in space claim, right? There are certain decisions I'm making when setting up a problem in space claim that allow me to mesh easily, but I also make the decisions because it eliminates additional complexity in the mechanical interface. So particularly, that would be with regards to like shared topology, so shared nodes in the interface. There's a way in which that just removes the number of contacts I have to apply manually or automatically, and that directly relates to decreasing my percentage of having an error in the setup. Okay, so meshing basics. So I'm going to kind of just walk through a couple slides on basics, and then I'm going to step into some of the examples I put together. So once again, feel free to interrupt me with any questions, either via the chat window or just chime in on the phone. Okay, so first and foremost, it's beneficial to understand the different really methods ANSYS has for meshing. Primarily, there's 3 to 4, depending on how you define it. The most automated and the one with the least amount of control is the adapted method. This is, honestly, it's from my perspective, it's not recommended, right? From my perspective, when you're running an FEA analysis, the user and the analyst running that job should have full control of every feature. There are times where adaptive is probably acceptable, but generally, even if it is, I will switch it off and then automatically apply my mesh control so I know exactly what's happening, exactly what the sizing is, and I'm not just specifying finer or coarser. So then if we do turn adaptive off, the other methods that become available that I'll speak to are really, and these are global methods, and then we have more local methods, are this idea of curvature meshing and proximity meshing. So I'll go into detail into what those are in the next couple slides. So curvature sizing function. So essentially, if you have curvature set, what's going to happen is the mesh, when it sees a curve, is going to want to refine that more than potentially the geometry surrounding it, right? And generally, that's defined by this curvature normal angle. If I have a circle, right, a circle spans 360 degrees. I can specify with the curvature function, hey, I want to have an element every 30 degrees, right? If you're every 30 degrees, you're going to have 12 elements around the entire circumference. So it kind of specifies the fineness relative to the curve, right? If you have a 90-degree fillet, you'll have 3 elements across that fillet, and kind of et cetera, right? You can see here, curvature is off in this case, curvature is on in this case. The right picture could actually be achieved with curvature on. You would just have, let's see, 1, 2, 3, 4, 5, right? So 360 divided by 5 would achieve this mesh coarseness, right? But generally, when I'm using curvature, I'm using it because, let's say I have a lot of sheet metal and I want broad spans of just blank sheet metal to mesh much more coarsely than near holes, because I know oftentimes at near a hole I'm going to have a stress singularity, and I want to have the impact of that stress singularity drop off quickly. So if I turn curvature on, I'm going to get finer elements around that hole, and so I can get a much better idea of what the stress is near that hole, assuming there's like a bolt there or something. Okay. Proximity, I'm just going to touch on proximity. Generally, proximity is used much more often for like fluid analyses, where small gaps or fluid flow through small areas relative to a boundary matter, right? For structural simulations, let's see, in 2 years, I've never used a proximity control, right? I've used curvature on a pretty regular basis, but proximity I almost never turn on. But so what proximity does is it essentially says, hey, we're going to monitor how close different features are to one another. And then if a feature is close in proximity on, we're going to mesh, more finely mesh the region between the features. The assumption being that the features are going to interact in some way to create a higher stress, or in fluid case, maybe a high flow rate, things like that, right? So you can see in this case, with the proximity control, you can specify number of cells across a gap. Here we specified 4, so you get 4 elements between these two features, which are the wall and the hole. And here you get 12 elements between the wall and the hole because you just specified more elements across that gap. But once again, generally for static structure, or really for any structural dynamics problems, proximity is very rarely used. Okay. In terms of element, what I'm going to call linear and quadratic elements, or in the past, ANSYS has defined this as kept mid-size nodes or dropped mid-side nodes. So essentially all this defines is the ability of the element to plot a certain stress distribution inside of it, right? So generally for a linear element, so this is an element without mid-side nodes, you can get a linear stress gradient across it, right? For quadratic elements, so elements with mid-side nodes, you can get a quadratic stress gradient across it. So as you can imagine, if you have a region with a very high stress concentration, it's going to take dramatically more linear elements than it would to take quadratic elements to approximate that stress concentration, right? Because you essentially have to linear increase up to that stress concentration rather than just using a much more exponential approach. So generally, what I would say is tetrahedrons, always quadratic elements. Essentially, linear tetrahedrons are overstiff, and unless you use an incredible amount of them, it's going to be the kind of incorrect answer. For hexahedrons, it's okay to use linear hexahedrons, assuming you have enough through thickness and you're not necessarily interested in stress concentrations if the mesh is too coarse. Sometimes what can be a good idea is if you're looking to run your problem quickly and efficiently the first time just to see if it runs and generally what the result may be, you can always use linear elements first, run it, and then once it runs, you can kind of review the results, say, okay, this looks like it's set up properly, and then just go into the mesh controls and switch to quadratic, and then run kind of your quote-unquote more final run to account for that. Okay, so then additionally, right, in your mesh controls, you have kind of allowable mesh criteria or mesh quality that you can define. Generally, the default is standard mechanical, right? So standard mechanical essentially, when it meshes a body, tries to allow for elements that have quality greater than 0.05, and potentially if an element has a element quality of less than 0.05, the mesh is going to try to iterate a couple times to remove that. If it can't, there's potential that poor quality element could cause the run to fail, right? You can always increase the aggressiveness of the quote-unquote allowable for the element quality. This will just, I mean, obviously, if you have better element quality, you're going to have a better solution, a better simulation. But for those jobs where it becomes more important to have good element quality, like large deformation, right? If you can picture, you're going to have elements that are being distorted much more than you would with a linear elastic problem, right? If you're going to distort a very bad quality element even more, it's going to get even worse, right? So that's somewhere you might need better element quality, and this aggressive mechanical setting will essentially tell the mesher, hey, you need to track this and you have to try for better than you normally would. Okay, so the three things I'm going to talk about, I started talking about these a little already, are method controls in ANSYS, sizing controls in ANSYS, and then inflation control. All these other ones, these are the ones that I've used maybe 1% of the time. pinch maybe a little more often, but once again, that's something you can generally fix in geometry and you don't need to fix it in meshing. We do not want to be modifying geometry in the mesh control ANSYS. That's not really its purpose or intent. All right, the purpose of space claim is to modify geometry so it's much easier and quicker. Okay. So this is just going to walk through methods. So the methods can be applied just to multiple bodies. If you just start off and then insert a method, it's going to apply as automatic. And essentially what that's going to do is it's going to either look to see if a body can be swept, and I'll talk about what sweeping is. If it cannot be swept, then it's going to mesh the body with TETs, specifically patch conforming TETs, and I'll talk about the difference between patch conforming and patch independent. So generally, the reason you would use an automatic method, right? ANSYS uses automatic by default. Really, the reason you'd use an automatic method is if you're going to change the element order for a specific body. Other than that, you're going to be using a different method. Okay, so the methods available for 3Ds and then 2D bodies. So for 3D bodies, we have tetrahedral meshing, patch conforming, and patch independent. Right, I'll talk about those. And we have multi-zone, hex dominant, and sweep meshing. Generally, from a purely solution size perspective, my goal is always to mesh with multi-zone or the sweep mesher. And obviously there are many times that those won't be able to be applied, and so then you just kind of fall back to tetrahedrons where necessary. For 2D bodies, 2Ds, you're talking shell bodies. These are much simpler. Automatic method is pretty much always better. Questions. Let me read this real quick. So the question is, which element order produces smoother contact results? I find quadratic elements tend to concentrate contact pressure on nodes. So the short answer is it just depends, right? Especially for contact results, it's much more a factor of element refinement as well as the method the contact uses to detect the other contact. So the default method is Gauss points, which potentially can concentrate contact pressures on nodes or they're projected to nodes. Right? If you want to have a better pressure distribution across that contact, you could switch that to, I think it's nodal projected from target, and that will kind of better smear the pressure across an element. Or you can just go ahead and refine that contact surface, right? And that should smooth out those contact pressures that you're seeing wrong, right? And generally, right, so we treat contact pressures, really any contact result, similar to a stress concentration. If you're truly trying to get an accurate answer, you have to run a mesh convergence study, right? You should be able to refine that mesh continually until you see the pressure, or generally looking at pressure or friction force, whatever criteria you're looking at should converge to a value. So if it's not done converging, that may be what you're seeing, where you're seeing concentrated contact pressure on nodes. So thanks for that question, John. Hopefully that answered. If not, feel free to chime in and say, no, that made no sense. So let's see. So jumping back over here, generally for shell elements, the automatic method is almost always going to be good. If I ever see triangle meshes on shell elements, like solely triangle meshes on shell elements, I'll generally clear that body and remesh it. And that will usually remesh with quad dominant, right? Triangles are just used really to interface between different quadrilaterals and like expansions and contractions in the geometry. Okay, so tetrahedral meshing, we have patch conforming and patch independent, right? The broad difference here is patch conforming. It's going to conform to boundaries on the geometry, right? So if we can see in this middle picture, we have boundaries at the fillets, we have boundaries between multiple fillets, kind of scattered throughout the geometry. The patch conforming method is going to respect that. And you can see here, you're always, let me see if I can get, you're always going to have, sorry, the gray doesn't show up very well, elements that kind of stop along all the lines that you see in the original geometry. Whereas the patch independent mesher, it's going to the extent that you tell it, it will ignore those boundaries and just mesh the body as if it was one continuous surface, right? So you can see in the region of interest, particularly this center section, none of those lines are remaining after the body is meshed. Generally, it's a little, you got to be very careful with the patch independent mesher, primarily because it can potentially blow away geometry that's important. Usually what I'll do is if I'm seeing a region where I'm getting very small elements due to, let's say, tiny faces or something like that, rather than switching to the patch independent mesher, what I'm going to go do is go back into my geometry and I'm going to either merge a couple faces to get rid of that small surface, or I'm going to go to, it's not shared topology. There's a way in which you can tell ANSYS, hey, look at these two surfaces as one. And I'm blanking on the name at the moment. So that would be the other option. So, and it comes down to a control thing, right? Anytime I see the simulation having more control than me, it gives me pause for concern. So it's the same approach. Generally, I have the same approach if I'm looking at automatically signing contact bodies. That's almost never going to happen because then I lose control. Then I have to go individually one by one through the contacts to try to determine, was everything applied correctly and was anything missed? It's the same idea with patch independent. If I mesh something with patch independent meshing, I need to go back in and kind of thoroughly examine the body to make sure geometry that I'm interested in wasn't removed. So rather than doing that, I'll just fix the geometry in the first place. Okay, so hex dominant meshing creates a free hex dominant mesh. So it's generally intended for bodies with large volumes. From my own personal opinion, I do not recommend this method. What you'll likely see when you mesh with this, and I'll show you in my examples, is a hex dominant method tends to create much worse quality or much lower quality elements than you get otherwise. And so rather than meshing with a hex dominant mesh, I will typically go into a body and just slice it up to get it swept mesh, or slice it up to the point where it can be multi-zoned, or I'll just go back to TETs, because usually I'm not willing to allow the poor element quality that the hex dominant creates, right? So that's just something to track. It's not terrible. If you want to use hex dominant, just make sure to review the element quality statistics beforehand and make sure they're acceptable. Okay, so swept meshing. So there's kind of a number of different ways to sweep mesh. Essentially, what a swept mesh does is it looks at a face. So in this case, in the bottom left, you know, the red face is a source, and it says, okay, can I take this face, mesh the face, right, and then kind of project that around the entire body, right? So here you can see it has continuous curves. This would be very similar to like a loft operation in CAD, a not too complicated loft operation in CAD. But it just projects it along the body, and then you just get this kind of mesh face cutting up the body along its entire length. This can be done really anywhere you see that continuous body occurring. So for instance, for this part potentially can be meshed with a swept mesh 6 different ways, right? So you can sweep it from top to bottom, bottom to top, along the arc like it showed before, or you could sweep it from the inside curve out or from the outside curve in. Any of them are acceptable, right? The reason that sweep meshing is really desirable. It's just purely from an efficiency standpoint. Anytime you can mesh with hexahedrons, it's generally more preferable and it's going to be more efficient than meshing with TETs. And particularly from a swept mesh, oftentimes assuming your sizing controls are appropriate, you're going to get better element quality with a swept mesh than you would potentially with some other methods. Okay. Okay, we're almost done with the slides, so then I'll switch more to the more interesting stuff. Okay, multi-zone. So multi-zone method, essentially, it's going to look at a body and it's going to say, okay, is there a way in which I can discretize this body so that I can make it into multiple bodies that are all sweep meshable? And potentially it can also say, are there ways in which I can discretize this body so I can have sweep meshable bodies and the remainder I can TET mesh or hex mesh or something like that. So multi-zone will always work on swept bodies, right? That's what it's looking for in the first place. It's always going to work. There are some benefits to it that I'll talk about when I kind of pull up my demo. But I would say prior to just assuming TETs, if you can potentially see a way that body can be broken up, it's worth trying multi-zone meshing. In general, you get fairly good element quality results with multi-zone. And multi-zone is generally also trying to mesh with hexes, and so it's going to be an efficient math. So you can see here in this example, right, this block is able to be broken up into really 2 cylinders and then a block with 2 holes. And so you can see in the final mesh, you have the cylinder faces coming through the surface, and then you have a continuous mesh through the block. Element sizing, so you can specify element sizing along an edge, element sizing on a face, element sizing for a body or a sphere of influence. So for a specific volume, you can specify element sizing. And then it's important to know you can turn element sizing to soft or hard from a control perspective. So essentially soft says, hey, mesher, I'm kind of recommending that you mesh this with this sizing constraint. There's times where the mesher is going to ignore that, right? So if you want that to be followed, you need to change that variable to hard, right? And then it's going to say, hey, mesher, you must mesh this with these size constraints. Sphere of influence just meshes a body or a volume more finely based on the specified sphere that's shown on the left in red. And then inflation, so you just define inflation layers. In this case, you're inflating from this edge in small layers. The reason you would do that would be potentially to capture stress concentrations near a hole or things like that. Periodically, I do find myself using inflation, and so I have a couple examples of kind of how to apply that. I think this should be the last one because I want to get to the demo. Okay, perfect. So what I set up here is just a large random number of shapes in space claim. So there's a couple of things I'll talk about as I walk through each of these. So I'm going to be jumping back and forth between space claim and ANSYS Mechanical. So let's see. So first and foremost, I've created a number of hemispheres, right, that are open on the bottom. And then I've meshed them all in different ways. So what I want to kind of show in this case is there's never one option for meshing, right? There's always multiple options. What will make your job easier just understanding how the different mesh controls work, so you can leverage those options appropriately. So let's just walk through these hemispheres and I'll go over how I meshed them. So in this first case, right, so in my first hemisphere, this is purely just meshed with tetrahedrons. And you can see I've meshed one through the thickness. It works, right? Tetrahedral meshes are always going to be able to work regardless of the complexity of a body, right? That's assuming that your body doesn't have really bad geometry that prevents a good mesh. So this is, if you can't get a mesh any other way, always just default to tetrahedral meshing. The next body that I meshed, I use a swept mesh, but particularly I use a swept mesh that is called a manual thin. So what a manual thin does, essentially it's going to mesh from the outside in, because I specified it, hey, that your starting face is this outside face, and I want you to essentially mesh the outside face and then project it to the inside face. And so the benefit of this is this body is not sweepable any other way without cutting it up, right? But with the manual thin method, you can see I get really nice surface mesh and I get nice 3 layers through the thickness, which may be important to truly capture the stress gradients that I'm going to experience on this body. And I have a very similar part here, mesh with manual thin as well. What I wanted to get across here is that you can see the wall thicknesses are much greater, right? Just because it's called manual thin doesn't mean it can't be applied to thicker walls, right? So just keep that in mind. It's a pretty powerful tool to have in your toolbox. So the next hemisphere I have, so this hemisphere is fully swept mesh. So what I did is I essentially broke up the body such that this kind of portion of the hemisphere can be meshed, swept mesh along the outside curve. Same for the green section. And then for the blue section on the top, this can be meshed just through the thickness, bottom up, top down. And so one tool that ANSYS does supply to see if a body can be swept mesh, if you go to mesh, right click on it, show, and then look at sweepable bodies, you can see here that entire body is green, right? That's an indication that, hey, ANSYS says this can be swept mesh, go for it. And the other thing I did here, which is important, and this is a very powerful tool that if you're not leveraging, I highly, highly recommend it, is you can see in this case, all nodes are shared at all interfaces. So at the interface between these two curves, as well as the top body and the surrounding curves, I have shared nodes along all those interfaces. What that means is this is essentially represented as one body. But the benefit is I no longer need to specify any connection in my ANSYS branch, right? I have no connections represented here, but I still get shared nodes. So that's powerful because anytime I have to add connections, there's a risk that I'm going to apply it wrong or that I'm going to miss it. Let me briefly just show you how to apply that. So this is a space claim feature, right? So essentially, if I have my chopped up hemisphere, if I go to the tab Workbench, I can currently show my shared faces and edges. But to actually share it in the first place, all I have to do is I've chopped it up. Then I'm just going to hit share. It's going to look for adjacent faces and edges. It's going to show me, hey, do you want to share these faces and edges? I'll hit share. And now the mesh is automatically going to share nodes along these interfaces. And it's going to share them well, right? There is the node merge capability in Mechanical. Oftentimes, we're going to see with the node merge capability is it's going to either miss nodes that should be shared, or when it shares the nodes, it's going to end up creating very poor quality elements, right? So the shared topology is a much, much, much better route. And this can be used for any number of things, right? I have a couple other examples where let's say I have a weld that's joining a body together. I can use shared topology to represent that weld joint, right? A weld fuses two metals together, it's essentially one part. By using shared topology, it removes the need of having to apply contact, but it also is going to decrease the number of stress concentrations that are going to exist in the model. So I can do that both for solids, I can do it for shell elements, for both, let's say, in this case, a fillet weld, and then on the right, this would be comparable to like a lap weld, right? This is all using shared topology. So once I do this, I don't need to apply any contacts. And so I've had parts with, or simulations with thousands of parts where I end up with thousands of parts and thousands of welds, where at the end of the day I might have 10 different contacts, primarily because I've very much leveraged the shared topology capability. So I really, honestly, I cannot stress enough the value of this tool. So if you have not used it, play with it, and you will see tremendous value and efficiency increases. Okay. Okay, so the next hemisphere is meshed with the hex dominant method. And what I'm going to show you, so I have two bodies here. So this body, this hemisphere, and this body on the right are both meshed with the hex dominant method with similar size controls to all these other hemispheres. And so what I'll show you, and this is what I was talking about earlier, is essentially if I look at my element quality statistics, right? So to turn that on, it's just under quality, mesh metric, element quality. And then what I'll do here is by default, this is set up such that there's 10 bars across the whole element quality range, right? What you can do to see kind of the quote unquote worst quality elements is I will typically, usually I'm not willing to accept anything less than 0.05, right? So in this case, I would find this element or elements that are below 0.05 and fix it. But in this case, I just want to show you kind of the potential risk with the hex dominant mesher. So here I'm just going to look at elements between, with element qualities of 0.04 to 0.2, right? 1 is perfect. 1 would be a perfect hexahedron. So if I update this, I can see there's 88 elements between 0.04 and 0.2 element quality. And then I can go to my graph and I can just click on it and see where they are. And if I look, right, very quickly we can see pretty much all my worst quality elements are occurring where I use the hex dominant mesher, right? Most of them are an acceptable quality to probably get an answer, but there are better methods out there. So essentially it's like, just my recommendation is steer clear of the hex dominant mesher, and unless you really have no other choice, and if you have no other choice, then analyze the element quality closely to make sure you're not going to hurt yourself in the future. Okay, so those are the hemispheres. The next thing I wanted to show is this little part over here. So this could be a piece of sheet metal. It's probably the most applicable example. But essentially, I have just kind of a curvy part with a little flange in the end. And if I go to mesh and say show suitable bodies, you can see this part does not show up as sweep meshable. However, it is, right? So this is sweep meshable with the manual thin control. All right, so if I find where that control is, right, I can click on the body, go to mesh controls for selected body. That's going to say, okay, here's your sweep method. Essentially what I've done is I have my manual thin, and I have specified two faces as kind of the surface to sweep through the body, right? So if I click off of this, so you can see the red is what I've specified, and it's going to sweep through the body. And the resulting mesh that you're going to get is a very clean mesh with good element quality. So this is a case where the mesher didn't think it was swept meshable. It is, and especially if you are trying to use solid sheet metal bodies in your simulation rather than shell elements, the manual thin mesher is going to be your friend. Okay, next up on the docket. Real quick, I'll just touch on kind of these bodies that look mildly like bolts. I've meshed these a few different ways. So the one on the right, This is meshed with a multi-zone mesh, and so you can see it's essentially broken up the body so that we have the primary cylinder, and then we have the surrounding portion of the head. Right, I can achieve pretty much the exact same thing if I chop up the body and sweep mesh it, but in this case I had to chop up the body 3 different ways to get that sweep mesh. And then last, right, anything can be tetrahedron meshed, so that's what I have on the left. Okay, so next step. So if you are working in a company that generally deals with sheet metal bodies, what I recommend, if you're ever running an analysis, usually it's always beneficial to remove radii prior to creating a surface from a sheet metal body. Right, these two parts right here are essentially the exact same shape. However, one I left all the fillets in there, and the other I removed it. Right, and depending on the mesh control, right, depending on if you have a mesh control that respects curvature, right, that is going to very finely mesh the curves because it's trying to capture it accurately, versus if you just remove them, you get a much coarser mesh for the same part that's going to be more efficient, right? And I can say from experience that having these fillets in here is not going to impact the resulting stress concentrations really at all, right? If you're truly genuinely cared about it, you can always do a test case where you have 2 parts like this, apply the same loads, and really deeply analyze how does having the fillet there and not having it there impact the resulting stress resulting stress on the body. And then let me talk to how to do that, right? So it's a very easy process to remove those in SpaceClaim. So if you're looking to prepare your geometry for meshing, so let's say I have a very large sheet metal structure that I need to analyze. By default, because any company is doing their work in CAD systems and they need to create drawings, you're going to have full curvature defined, you're going to have solid body thickness defined, you're going to have all these things automatically defined. So we kind of need a quick and efficient way to reduce that geometry to a point where it's meshable. And usually when you're dealing with sheet elements or sheet metal, we want to reduce it to surfaces so we can mesh it with shell elements, right? So over here, what I've done is I have really 3 different phases of the same part. So this middle one would be the original, then it'd be with removed curves, and then it would be as surfaces that I could later mesh with shell elements. All right, so to do the reduction in SpaceClaim is very easy, right? All we're going to do is if I click on a fillet, I can go over to selection, and I can select all rounds on this body equal to or smaller than what I selected. All right, so I click on that, hit delete, it deletes them all, right? And then now you're left with a body without the curvature. And then I go to prepare, mid-surface, click the 2 opposing sides, mid-surface, and now I'm left with my shell body. This shell body automatically has the sheet metal thickness associated with it, right? So this is 1 millimeter thick. And that's kind of how you walk through initially, just reducing sheet metal to surface elements. And so from the perspective of meshing those things, right, we have there should be one more there. No, whatever. We have the final body here is going to be very smoothly, uniformly meshed. We could mesh with solids, but once again, solid elements are generally going to cause, well, generally for solid elements, depending on the stress or the deflection you're seeing, you usually want more than 1 element through the thickness. If you're experiencing only bending, then 1 element through the thickness is acceptable, but that is almost never the case, right? So you usually want at least 2 elements through the thickness, if not more. Okay. Let me talk to you. So it's almost 11:52. I'm going to wrap up here in 1 second. So then let me talk to inflation controls real quick. So inflation controls really work well primarily on bodies that can be multi-zone meshed or tetrahedral meshed. Right, so we can see here essentially I have the exact same body and I've applied inflation controls to the inside of the hole. So in this case, I'm telling, hey, I want to inflate this mesh out away from this hole for a certain number of layers. And I'm doing the same thing on the left body. Right, this method is generally not going to work for swept meshes. It may work for hex dominant meshes, but once again, I would not recommend using hex dominant meshes. So if you want to inflate around a hole or something similar, go to multi-zone or go to tetrahedral meshing. Okay, curvature. This is just an example of what I showed in the slides. So we have two plates, exact same controls, except for the curvature angle is defined slightly differently. So you can see here, I have this circle in the middle of the plate, much more refined than the circle on the left. The benefit is the circle on the left is going to be much more efficient from a standpoint of just number of elements, right? And oftentimes, if I'm running a job with a lot of holes, usually I'm okay with six elements around a hole. And if I'm truly interested in it, I can just go to that specific hole and add more elements, right? Because you'd be surprised how quickly it doesn't look like much between these two plates, but you'd be surprised if you have many of these holes, how quickly the number of elements, the difference of the element numbers between them adds up. All right, so this job on the left, let's say it's going to total 200,000. Job on the left could be 350,000 elements, right, which has a dramatic impact to runtime. Okay, last but not least, and I showed you this a little bit earlier. So we have our body sizing or edge sizing or face sizing controls we could use. The one I really just wanted to touch on was sphere of influence, right? So to establish a sphere of influence, and this is just going to have localized refinement anywhere the sphere touches that's highlighted blue. What we need to do is just add a coordinate system that defines, hey, I want this to be the center of the sphere. Then we add an edge or a sizing control. We're going to specify a sphere of influence, the relevant coordinate system, the radius of the sphere, and the element sizing within that sphere, right? And then we can see is if I take a section of this sphere, I'm actually going to show the elements. You can see everywhere in that sphere has been refined, right? And you could just refine, it's not going to show both at the same time. You could just refine the surface, right? And then you get slow expansion out until it is at the default element size. It's just wherever you want to see, right? Here, if I'm trying to capture, let's say there was a fillet here and I want to see how far that propagates, that stress concentration propagates in the material, I would probably do a sphere of influence, likely not this size, but that would capture refining the elements through the body rather than just on a surface. Let's see. So that's, I know that's a whirlwind, but that's general control and general recommendations, right? Honestly, the largest recommendation I can make with regards to meshing is all your work, not all, very heavily focus your time on preparing the geometry rather than just immediately taking the geometry and meshing it, right? Generally, the process I will take is I'll have, if you have the licenses available, I'll have SpaceClaim open in one window, and then I'll have Mechanical open in another. And I'll be doing my work in SpaceClaim on a single part, right? Kind of just reducing that geometry to the point where I want it. And once it's done on that single part, I will update Mechanical and just mesh that part just to see that did the refinement and reduction that I did on that part kind of achieve what I wanted it to. And if it did, great, and I can move on to the next part. And what that allows you to do is you're never going to get to the end of a large analysis where, let's say, you're just only spending your time in space claim. You get to the end of reducing this huge assembly, and then you go to mesh it, and you find that the rules of thumb or the refinements that you're doing for every single part all of a sudden didn't achieve what you wanted, right? By doing kind of the more iterative approach between space claim and mechanical, you'll prevent that. And by doing your reduction and space claim, it's just going to make the process a lot quicker. Use shared topology heavily. That's going to reduce the need for connections, right? Anytime we reduce those number of connections, it's beneficial. And those are probably the biggest recommendations I can make. Let's see. We did get one more question. So the question is, can you focus a bit on the output of the mesh quality graphic? What do I need to be looking for? What to avoid? So certainly. So generally, with the mesh quality graphic, so by default, you're going to have 10 bars here. Typically for structural problems, the mesh criteria that I'm interested in is element quality. There are, if you pull this down, there's a number of other criterias. They're just different ways to look at how deformed from perfect a cube or pyramid or tetrahedron is. But so for structural problems, I'm looking at element quality. And generally what I want to look at is first and foremost the lowest number on the x-axis. So when I'm meshing something, automatically I know I want all my elements to have element qualities of 0.05 or greater. And generally, I want the majority elements to have much greater than 0.05. Right? If I'm seeing that the majority of my elements have element quality values of, this should be 0.05 to 1. There we go. So if I'm seeing that the majority of my elements have element qualities at 0.5, I might consider where that's coming from and try to improve that. But so the first value to look at is this lower number. If it's less than 0.05, I would say spend some time to get it above 0.05. And then the way in which you do that is we want to find out, okay, where are my elements that are 0.05 or less, right? And so what we'll do is rather than having 10 bars, I just want 1 bar. And on this x-axis, I'm going to change this to 0, and I'm going to change this to 0.05. And I'm going to update the y-axis. So I can see in that range, there are 3 elements that are less than 0.05. So I'm going to go back to my chart, and I can actually click on the bar, and I can see, okay, in this body over here, I have 2 elements. Actually, I have 3 elements in this case that have an element quality of less than 0.05. And you can see if you look at these are pretty poor elements. If you look at this hexahedron, it's incredibly deformed. So I know I need to fix that, right? First way to fix it would be not to use hex dominant. You can see I have the exact same part on the left. Does not have that problem. You can try multi-zone. You can try chopping of the body. You can always just try just making the element size smaller, right? But there's a drawback to that from a standpoint of solution size. And those are generally approaches. And once again, you can click the other bar as well, and you see we have a also very poor quality tetrahedron. And then once you get the element quality all above 0.05, usually that's good. If I'm ever working in LS Dyna, I know I want all the element qualities above 0.2. It just depends, right? But 0.05 for most static structural, transient structural, modal, or vibe problems is acceptable as long as it's the minority elements, right? You want the majority of your elements in the upper ranges, right? So if I go back here to 10, you can see that is the case for the bodies I've created. The majority elements are shown at the upper span of this graph. So I believe, unless anyone else has any questions, I know I went a little over time, so I apologize for that. but that wraps up the meshing. So are there any questions? I know I kind of covered a large range of topics, but feel free to chime in with anything. Okay, well, you can always follow up with an email if you do have additional questions you think of later. But yeah, so then I'll turn it back over to Boz.
Yeah, well, thanks, Steve. It was a lot of information. I'm sure everybody appreciated it. Again, the recording will be available if anyone would like it. And then next week, we'll be doing another webinar. I will be sending out the invitation to everyone. So if you would like to attend, let me know, or if you know of a friend or colleague who would be interested, feel free to forward it to them. And that's all we have. Like Steve said, any questions that come up later, you can always contact us. And everyone, thanks for attending, and everyone have a good weekend. Take care.